Okay. Hello, guys. So it's been all very haphazard, but I am finally deciding to do the 2023 Chemistry NHT exam. So I've already done the MCQs. Um, cool. My goal is to get this done in under an hour and 30 minutes. So let's see if we can somewhat speed run this. Okay. Kombucha is a fermented tea that is produced by mixing tea, water, and sucrose with bacteria. The bacteria break down the sucrose. Um, so firstly, it'd be great if I could get the annotating feature, which it's not letting me actually write. Um, what's going on? Uh, oh, perfect. Okay, cool. So basically, what's happening is there the sucrose is being metabolized, okay, into obviously its um into G and F. Okay, so sucrose is a disaccharide that's made up of glucose and fructose. Now, fruit chemistry isn't really a part of the chemistry study design anymore. However, understanding the types of reactions and things like that is really important. So it says name the type of reaction that breaks down the sucrose into simpler molecules. Generally speaking, when we're going from sucrose and we're breaking it up, we do it under a reaction called hydrolysis. Okay. Lysis means split and hydro means water. So we're basically using high water to split um to split the molecule up, right? So it's actually in the name. And then condensation is the opposite reaction, and that's when we're turning simpler molecules into sucrose, right? And obviously in condensation, uh we are what are we doing? We're producing water. Okay, cool. In the kombucha process, bacteria produce cellulose, which is removed prior to bottling. State why removing the cellulose makes no difference to the nutritional value of the final product for humans. So, basically speaking, the reason why, it doesn't make any difference whether we have cellulose or not in the kombucha is because simply speaking, we cannot digest cellulose. If we cannot digest cellulose, then we cannot absorb cellulose, right? So, for those who don't know, cellulose is found in plants. It actually makes up the cell wall of the plants for those who've done biology. And the reason why a lot of animals eat grass and we don't is because they actually possess cellulase. Okay. So simply speaking, humans do not possess cellulase enzyme, which is required for cellulose digestion and absorption, right? So if you're not able to absorb the cellulose, then obviously it won't make any difference to the nutritional value of the final product. Um, a kombucha manufacturer is considering adding vitamin C or D to the kombucha. Explain the advantages of choosing vitamin C over vitamin D in your answer. Use your understanding of the chemistry that you've studied for the year. So here, couple things, okay? So I don't think they have vitamin C there anymore. That's a bit of a shame. That's okay. So, oh, because this was of the previous study design, I think. Oh, that makes a bit more sense, maybe. Yeah. So, here, what you guys need to remember is vitamin D is a fat soluble and it's a non-essential vitamin. Okay. So it stays in our bodies. And then basically, the way in which we get vitamin D is via sunlight, right? Then sunlight basically activates a system in which in which we increase the amount of vitamin D in our blood. Actually, interesting fact, a lot of Melburnians are very deficient in vitamin D because obviously we don't get as much sunlight here. So I think the best benefits of why we want vitamin C is firstly, it's an essential item. It's an essential vitamin because it's water soluble. Um, and yeah, basically it doesn't get produced by the body. And so we need external sources of it, such as oranges and things like that. Yeah, I'd say so. So I'd say vitamin C, given that given that it is given that it is a non-essential vitamin, given that it is a non-essential vitamin, um, it's a non-essential vitamin, and thus something like, sorry, I'm having a bit of a brain fart. Thus we require a constant external source of it. This is due to vitamin C possessing multiple hydroxyl groups in its structure, which cause it to develop hydrogen bonds with water and thus um, being soluble in water and thus it being easily passed out in bodily fluids. Something like that. Um, so I guess what I've done here, I know it hasn't been with the greatest, most chemical efficiency. I basically talked about how vitamin C is it's a non-essential vitamin. Wait, sorry, it is an essential vitamin, sorry. And we require a constant external source of it. And then I sort of referred to the chemistry, or at least attempted to do so. Okay. So vitamin C, again, maybe we could say here instead, given that it is a soluble and essential vitamin as opposed to the fat soluble vitamin D. So I want to make reference to the vitamin D. It's really important whenever we're looking at the comparisons. Um, bef you know, where Yeah, it's really important that whenever we're looking at the comparisons between two things that we always include the other thing, right? So vitamins act as coenzymes, describe the role of coenzymes in enzyme reactions. So the two things that are really important to always add whenever we're discussing coenzymes, okay, is one, the structural aspect of it. So it basically augments the active site, basically makes the overall active site more complementary to the substrate. And it also acts as an intermediate carrier of electrons and H pluses and other sort of functional groups. Okay, so coenzymes augment. I love that word. Augment the active site, making the overall um, structurally, maybe we can say structurally augment making the overall active site more complementary to the substrate, and moreover, coenzymes can act as intermediate carriers of important functional groups, such as then your electrons, your H plus ions, and things like that. Um, yeah, so I think that's all you really need. That's basically um, that's what they are there for. Cool. So basically, what I've discussed here is the structural aspect of coenzymes and the chemical aspect of it. If anyone doesn't know what I mean by what I mean by coenzyme structurally augmenting the active site. Basically, what that means is if I have an active site like this, right, but my substrate is this, basically what a coenzyme does is it basically attaches itself. So that is what we call the coenzyme. So now the active site looks more complementary to the substrate, and therefore the reaction can actually go ahead. So without the coenzymes actually there, it's actually very difficult for the reactions to go ahead. Look, in terms of relevance to the current study design, I don't think it's too relevant. However, maybe hydrolysis and condensation is good to know about. All right, this stuff very, very important to know. So consider the reactions shown in the diagram below. State the internal IUPAC systematic name of compound R. I think the biggest problem that I see people doing whenever we're looking at questions like these is they just go straight into like writing the names and the structural structures and whatever into the boxes. Okay. However, it's really important that you're writing it in the form that they want. The best way to do that is to just answer A. Just go down and treat it like a normal question. So we need to write the IUPAC name of compound R. Of compound R. So here, whatever side is facing, so this oxygen basically signals the start of the alcohol. So there's one, two, three. So it's propanol that it started with. And then there's two carbons here, which indicates the acid. So it's just propyl ethanoate. And then the functional group in compound M. So that's a COH. Because that's at the end, it's an aldehyde group. My handwriting definitely needs to improve. But by the way, if it was in the middle of a compound, it would be a ketone group. So they're basically the same thing. That's even worse. Cool. Identify the reagents required to convert compound M to compound N. Um, so as we can understand, this is probably propanol. Okay, it just has one oxygen, which means compound N would be ethanoic acid, right? So we are basically converting an aldehyde into ethanoic acid. For those who don't know, basically this would have been ethanol first, then oxidized to form compound M, which is ethanal, and then further oxidized to form ethanoic acid. Okay, so normally speaking, we want to add oxidizing agents. Now, our two lovely oxidizing agents that we always love to include here is either H plus MnO4 minus aqueous or H plus Cr2O72 minus aqueous. Now, the biggest thing here is sometimes I see people putting like a K plus here. That is wrong. Okay, so it's really important that these are acidified permanganate ions, okay, or acidified dichromate ions, because as ethanol is going through oxidation, what's going through reduction? Remember, for something to go through oxidation, there must be something else that's going through reduction, right? That's why it's called redox, right? So if this is going through oxidation, then these are going through reduction. This forms Mn2 plus, and this forms Cr3 plus. And in order to balance the hydrogens, we need H pluses there. So the reaction can't go ahead, okay, if our oxidizing agents aren't acidified. So it's really important that you guys are adding the H pluses there. Um, cool. So just one of the two there. Don't put both, please. Okay, we don't want two oxidizing agents. Cool. So we know that compound N is going to be ethanoic acid. I draw the structural formula of compound N. So it's good to know what form that they want it in. Okay. So ethanoic acid is pretty chill. Even in your practice exams, please write your actual H's. What produces compound Q? Okay, so we have here propane. And basically, whenever we have an equation involving propane, I mean, here it's very clear that it's being turned into a haloalkane, so then it can actually go towards the process of becoming an alcohol. Um, as a general rule of thumb, I mean, I don't know if this is like always going to be the case, but generally speaking, whenever you're starting with an alkane, there are always going to be substitution reactions, right? Because what's happening is when we add it with Cl2, one of the Cl's here is going to substitute with this. Okay? So one of the Cl's and the H's are going to substitute, and then they're going to form HCl as a byproduct. Okay, so it's a substitution reaction. If it was an alkene, so if it was an unsaturated hydrocarbon, then most of the time it is an addition reaction. So even if you don't know much about this and you want to take a quick guess, just think about, well, is it an alkane? Okay, cool. Then it's probably going to be a substitution reaction. Or it's an alkene? Okay, it's probably going to be an addition reaction. In these types of reactions, we don't really see, um, yeah, we don't really see alkynes that much. Compound Q is converted to compound P when reacted with water. Compound P, draw the skeletal formula of compound Q in the box provided. So they basically would have formed, so basically, they basically would have formed a haloalkane. Okay. So I like to draw it out, the structure first, before actually writing the skeletal formula. But basically speaking, skeletal formula is really simple. I just look at the structural formula whilst writing the skeletal formula. So it'll just be this, and then Cl, or this, Cl. Okay. So really easily speaking, the whole point of skeletal formulas are to not show the C's. Okay. So you can show every other functional group except the C's. So here, each vertice basically represents a carbon. So carbon, 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 there's three carbons, and then you've got your chlorine at the end. That's why it's so important to actually read the question because somebody could have easily just lost a mark there by just writing the structural formula. Does compound Q have a chiral carbon? So how many marks is it? It's 2 marks. So if it's 2 marks, generally speaking, you want to write the definition of a chiral carbon first and then justify why compound Q doesn't have a chiral carbon. So let's draw out the structural formula of compound Q. It's this. So generally speaking, each carbon here is connected to two hydrogens, right? And therefore, none of these carbons are connected to four different functional groups. Okay. Okay. So basically what we can say here is that chiral carbons are carbons that are connected to four distinct distinctly different, or something like that, functional groups. In one chloropropane, none of the carbons are connected to four unique functional groups, and thus, or maybe at the start we can say no. Oh, and thus, oh, actually, that's fine. And thus, compound Q does not, maybe we can put it in caps, have a chiral carbon. Ideally, maybe another way you can think about the marking criteria is 1 mark for saying yes or no. However, generally speaking, I don't know if they give out a mark just for saying, because if it's a 50-50, then I don't think they give a mark for that. So you have to really justify what the definition is and then say why there isn't. Okay, cool. So this is a galvanic cell question. Um, cool. So state the maximum cell voltage. Oh, this is a tough one. Um, so pretty stock standard. So you want to find Ag. Every time I see a silver sort of half cell, I always know it's going to be on top. I mean, it is really high. So Ag is here, and then we've got Ni2 plus, which is there. So that's 80 minus 0.2, 80 minus 0.24, which is 1.04 volts. Cool. I don't know if um yeah, I don't know if they require the plus, but I think it's okay. So here, I can't believe that's only 1 mark. Probably should be two. But basically, you need to realize that I'm gonna times everything. I'm gonna times the top equation by two because I know that the bottom equation has two electrons in it. So I've just times this top one by two. It's like how simultaneous equations work. And then I've canceled these out. So nickel is obviously going through oxidation. So here, basically you can see that This is basically what's going to be happening. So we formed a negative gradient here. So Ag plus is going to be reducing and nickel is going to be oxidizing. And then we just write that out. Again, for 1 mark questions, you don't really need to say too much. The best way to also check if you've done everything correctly is to just check the charge on on each side. Also, it's fine if you take up another line just to write the states. So there's 2 plus here because there's two Ag pluses and an Ni2 plus. Microbial fuel cells use bacteria to metabolize biomass. In a microbial fuel cell, the bacteria decompose biomass in the absence of oxygen through a process called anaerobic cellular respiration. Write the equation for respiration that occurs in the cells of the human body. So obviously, as you guys may know, um, this has recently come onto the studies design, but super chill. I don't know if we need states for this, but let's just be on the safe side of things. Let's just make this liquid. Um, cool. So yeah, it doesn't really matter that glucose is aqueous. So a lot of people would say, well, how would this still be like, whenever we look at combustion equations, the fuel's almost never aqueous. However, it's fine in this situation. On the axis below, sketch the energy profile diagram for respiration. Another thing that I really just want to mention here is that the x-axis can never ever be time. I think, if everyone can leave today's video learning one thing, it's just that this will never be time. Okay? The the energy profile diagram simply just indicates what the energy transfer between the system and the environment is looking like. There's no indication of how fast the reaction's going and things like that. Especially here as well. They haven't actually given us any enthalpy or anything like that, unless, let's just check. Biodiesel, bioethanol, that's fine. Hmm. Oh, there is glucose here. That's in aqueous. Okay, it's 2803. So on the axis below, sketch the energy profile diagram for respiration. So we basically need to show that there is an enthalpy change of 2803. So, as we all know, I mean, this is pretty obvious. Why do we eat, food? Why do we eat apples and all of our food is because to get energy, right? So obviously this reaction is gonna release energy. Another way you can think about it, well, obviously this looks like a combustion reaction, right? So you want to draw your standard sort of exothermic reaction. Please use a ruler. But I would say products here. I'd say my reactants here. And I think what my money mark here in this situation is writing the delta H, which is minus, what was it? 2803. Cool. Maybe let's also, cool. Yeah, make sure you guys use a ruler. But I don't think we need too much more than that. I don't even know if we need this because they didn't ask us to write the thermochemical equation. So maybe they just asked for a simple representation of whether it's an exothermic or an endothermic reaction. The MFC anode has bacteria growing on it. The bacteria decompose organic matter and produce H plus ions. So they're using bacteria to metabolize biomass. Okay, so basically this this is an anaerobic environment then probably. So basically what's happening is the bacteria is decomposing the biomass, which is, so this is the fuel, I guess. So biomass is being coming here. Then anaerobically it's being fermented. So this is like kind of like biogas is being produced, I guess. And then they're producing H plus ions and electrons. So it's basically working in the same vein as like, normal hydrogen fuel cells work, whereas where hydrogens oxidize, and then, H plus ions and electrons are produced. So it's the same thing kind of. The H plus ions are, going across the electrolyte. The bacteria transfer electrons directly to the anode. So they're probably going like this. And then so the electrons are being produced. They go through the external circuit into the cathode. This makes the cathode extremely negatively charged, which the H plus ions neutralize, and the oxygen collects both the H plus ions and the electrons to produce water. The bacteria, and then one half cell has oxygen bubbled into it. In the other half cell, oxygen is excluded. Okay, that's very important. So we have an oxygen-rich environment in the cathode environment, but we don't have oxygen here, right? Because we want the biomass to be anaerobically fermented. So write the balanced half equation for the reaction occurring at the cathode. So that's pretty much your stock standard reaction that's happening. Basically, if anyone's done biology as well, it kind of works very similar to how the electron transport chain works, right? Basically, the oxygen acts as a collector of the H pluses and the electrons, and then the water is produced. If you guys also don't know this equation, you can just find it in the data book. So it's this one. So it's really important, like you guys really need to know your equation. So this one, you also need to know its basic counterpart, which is that one. Okay, so these two equations are pretty much the exact same, except they're just in different environments. So that's your very stock standard one. Um, gas, aqueous, liquid. All right, explain why the two half cells are separated. So yeah, as I was saying before, the main reason, okay, is um, so the function of the cell requires the anode to not have any oxygen in it. So if we didn't separate the half cells, then the biomass would start aerobically fermenting, okay, which would not produce our H plus ions and electrons. So um, the functionality of the fuel cell relies on the biomass being anaerobically fermented or broken down. What are they saying? Decomposed, anaerobically decomposed, and as such, the half cells are separated to prevent oxygen from entering the anode compartment or something, the anodic compartment, the anode compartment, the anode compartment. This ensures that the biomass is not aerobically decom is not aerobically decomposed, as it would not produce H plus ions and electrons. Now, you could also go down, like, I feel like that's probably your best shot. Yeah, that's probably your best answer in this situation. I don't know if my second mark is quite there, but yeah, basically what I'm trying to indicate here is that, yeah, I just want, yeah. Um, cool. Um, cool. The other thing that's always good to keep in mind as well in any fuel cell is if there wasn't any separation here, right? So just give me a second, guys. Sorry. As I was saying, um, the reason, like another aspect that's really important to consider is for normal fuel cells, the best answer in this situation would also be like the very reason as to why um this is able to produce electrons is because they've been separated. Because if there was no separator mechanism here, then biomass and oxygen would directly react, and that would produce heat energy instead of electrical energy. So we want to produce electrical energy. So by having the half cells, we are able to facilitate the creation of an external circuit. Right. So there's a really good chapter in the Jollo textbook which talks about direct versus indirect reactions. And generally speaking, you just want to remember that direct reactions produce heat, indirect reactions produce electricity. However, for this type of reaction, I would say this is the best answer because it's actually referring to the cell itself. I'm not sure if they would really accept the biomass and oxygen directly producing to produce heat energy, directly reacting to produce heat energy. I'm not sure if they'd accept that. For the cell shown in the diagram above, state the feature that causes the overall movement of H plus ions across the membrane. So as I said before, the electrons are going to the cathode, making the cathode negatively charged. So the H plus ions need to go there to neutralize it. Um, as the cell progresses, electrons travel from the anode to the cathode, making the cathode negatively charged. To maintain electroneutrality, H plus ions migrate migrate across the membrane to neutralize the charge, which is then later picked up by oxygen or something like that. Yeah. Um, cool. State an advantage of MFC over the AgNi2 galvanic cell. So look, again, you can say, your stock standard, what is the advantage of a fuel cell over a galvanic cell, or you can make it specific. The one thing that comes to mind here is biomass. Okay. So biomass is a renewable um, source of energy as opposed to silver and nickel, which are non-renewable, as there are finite reserves of them, something like that. Um, cool. Um, Other things that you could have said is that obviously the galvanic cells, they rely on a stored set of reactants, whereas fuel cells, they will continue to produce energy because of the continuous flow of reactants. Yeah. The calibration factor was determined using electrical heater operating for 240 seconds. Cool. So, got your calibration factor. So it's VIT over to change in temperature. Is it? Yeah, so it's VIT over temperature. Okay, so you can see it in the um you can see it in the data book as well. So if you guys ever forget your equations, just literally refer to the data book, not that deep. Um so E so E so 3540 is basically equal to 6.5 times by, so that's V, and we're trying to find I times 240. They've already done it into seconds for us, 1.7. Therefore, I is equal to, yeah, so 3540, 3540 times by 1.77 divided by, so then that's equal, divided by 6.5. 6.5. Stop. 6.5 divided by 240. Why is this doing that? 240. All right. 4.02 amps. All right. Three significant figures, I reckon. 3SF. Cool. I don't know if we need any more working out for that. Um, a temperature increase. So basically, we have our calibration factor, which is 3540 joules. And then if we had a temperature change of 5 degrees Celsius, so generally speaking, it'll be energy equals to 3540 kilojoules times by 5 degrees Celsius. Oh wait, is it? Oh no, it's joules, it's joules, it's joules, it's joules. Okay, cool. I'm just gonna I'm gonna do it on my phone calculator because that was really annoying. 3540 times 5. All right, that's 17,700 joules. Now that was how many joules was released when we had 2.5 grams? And they're asking for 100 grams. So all we need to do is we need to say, well, 17,700 joules was released when we had 2.5 grams. So we just divide it by 2.5 and then we do it to 100. Because by dividing it by 2.5, we're finding out how many joules is released when we burn 1 gram sample of muesli, and then we just times it by 100. Or it's in joules, it's in kilojoules as well. So let's just times it by 10 negative 3. Um, Very lazy. Times by 100 divided by 1,000 and should be 708 kilojoules. Cool. It's little things like that that kind of trick people up. So protein, if you guys look at the data book, I think carbohydrates is 16, protein is 17 kilojoules per gram. So 20% of the energy content, so of the muesli is due to the protein. Calculate the mass of protein in 100 grams of muesli. So we would just do energy protein. So this is the energy that's actually delivered by the protein. It'll just be 20%, so 0.2 times 708. I wonder if they give consequential for this because it's a bit tough. What if you get the first question wrong? So that's 141.6. That's 141.6 kilojoules. And then the mass of protein would be that divided by 17. And so we can say with pretty decent confidence that would be 8.33 grams of protein. Yeah. State how the products of metabolism are used by the body to produce large biomolecules. So muesli, obviously, it has protein, as we've mentioned, but also has carbohydrates. So carbohydrates, I don't know. So state how the products of metabolism are used by the body to produce large biomolecules. All we can say um, is that muesli is broken down into constituent amino acids and glucose molecules into constituent monomers such as maybe amino acids and glucose molecules, which can then via condensation form proteins and glycogen storage and form proteins and you know other storage molecules, other and glucose storage molecules. I think that's fine. Is that a bit of a cop out? Or maybe I can just say glycogen. I don't know. I hate questions like these because it's like so obvious. Muesli is broken down, which can then, I think maybe condensation is probably the important part here, right? I mean, yeah, it seems like too easy of a question. Other than the chemicals produced by metabolism, with what else does metabolism provide the body? What is metabolism? Like energy? With what else is metabolism? Would it just be energy? So metabolism, why are we breaking down foods? It's so we can absorb it. So it's probably energy. I don't know. Not too sure about that one. Um, let's have a quick read of this. Or maybe can I skip it? I'm gonna skip it and I'm gonna come back to it. Oh yeah, I want to do that question instead. We'll do the experiment question at the end. So we can do, yeah, so we can do these questions. I won't do 10. So we can do 7, 8, 9. And then yeah, cool. Yeah, we can just do this experimental question at the end. That's okay. Um, cool. State the structural feature that is present in an electrolytic cell but absent in a galvanic cell. Um, Electrolysis. So I would say maybe um only one cell, only one half cell, only one cell, as opposed to two half cells. Okay, so electrolysis most of the time happens in one cell. Um, Whereas, like especially depositing copper, that's electroplating. Whereas galvanic cells happens in two. You could also say that electrolysis requires, you know, power, whereas galvanic cells don't. Standard advantage of using copper over platinum as the anode in the electrolysis cell used to deposit copper on PCBs. So, as I was saying before, it's electroplating. So basically what they're doing is this is our PCB, that's our copper. So obviously the electrolyte would already have copper 2 plus ions in it. But by having the copper as the anode, it basically ensures that we have a constant supply of copper ions in the electrolyte so that, the electroplating process isn't disrupted. So, um, so that copper at the anode is oxidized into CO2 plus ions, ensuring a constant supply of copper 2 plus ions, and thus and thus facilitating a good electroplating process or something like that. A a non-interrupted, an efficient electroplating process. All right, stock standard copper is at 63.5. So that's just a stock standard sort of um, what is the is it 63.5? I'm pretty sure it's 63.5. Copper is 63.5. So um basically you want to find out moles of copper, which is 5.08 over 63.5. I mean, these questions are incredibly easy. I mean, there's not much you need to do here. I mean, this should just be muscle memory at this point. Now, because copper, because this is what's happening basically, it's copper 2 plus 2 electrons to give copper. There's a, how do I say, 1 to 2 ratio between the electrons. So the moles of electrons would just be that times by 2. So it'd be 0.16 moles. And then the Q would just be that times by 96,500. I mean, it's really interesting, right? But the types of, things you would do for homework, like textbook questions, it's pretty similar to what you get in the textbook, the exam when it comes to these sort of questions. And therefore, time is 15,440 over 4. And that's 38060 seconds. Cool. Um, um, cool. Now it's two significant figures maybe because of this guy. So 3.9 times 10 to the power of 3 seconds. Look, I don't know. I would just cop the mark when it comes to significant figures. You've got, so here, two platinum electrodes, electrolysis. So platinum doesn't do anything. You've got 1 molar, so you've got water, you've got sodium, and you've got hydroxide ions. So let's highlight them and see what's happening. So that's the best way to do electrolysis questions, is to basically highlight your species and then reason with yourself, like what would actually be happening. So we want hydroxide ions to be by themselves, right? Like we can't do something like H2 and 2H minus because that assumes that we've got hydrogen gas on our hands, which we don't. So we've got sodium ions here. We've got water there. We've got water there. So it'd be these two reactions that are happening, right? Because that's the strongest oxidizing agent, that's the strongest reducing agent. Write the equation for the two half reactions that occur. So it'd just be that and that. Okay, I'm being lazy now, but make sure you guys write down the states as they are in the data book. All right, super easy question. I didn't think there was anything too bad with that. Very nice, nice and simple. Cool. Carbon, hydrogen, oxygen. So, generally speaking, whenever I'm looking at IR, I can instantly tell that this is an alcohol because it has kind of like a peace sign. So, alcohols tend to have a peace sign, whereas acids tend to have more of a sort of a MITS, sort of like a bit more broader. So, this is definitely alcohol. And we all know that this sort of straighter peak tends to be CH, and this tends to be OH in the alcohols. So identify the top type of bond in chemical P. So this would be OH alcohol. I don't know if you even need a. Oh no, it says identify the type of bond. Sorry, so you just say hydroxyl. Yeah, look, for IR, I don't really refer to the data book that much. I think it'd be a good idea to do just expose yourself to a lot of IR questions because what you'll find is you'll over some time you'll start to identify what different compounds look like. So what's the molecular formula of so the molecular ion has a very small peak at 88. So it's a hydroxyl. So if I know it's an alcohol most likely. We have CHO. So what I can do. This is the way I do it. You guys might, suggest a different way. I kind of just do trial and error. So I know that there's an oxygen there, so I just minus 16, which is 72. Now I've 70, so now the C's and the H's, I believe, make up the 72, right? So what I do is I tend to just mi keep minusing it by 12 until there's an appropriate number of hydrogens. So if I minus it by 12 times 5, then that's 60. So that's 12 hydrogens. So that's C5H12O. Um, well, that's probably, yeah, I'm actually pretty happy with that. Um, okay. And then if I do 72 minus 48, that's 24 hydrogens, which is not good. That's C4H24, that's not good. What about, oh yeah, and then if I do 72 minus 12 times 6, that's just 72, which is means zero hydrogens. So I'm pretty happy with that. So C5H12O is good. Can anyone let me know in the comments if there's any easier way? Um, I also understand that you can do something like CXH2X plus 2O. However, we don't know whether there's a double bond of the carbons. What's the thing here? So it would be 55.7. Should be 57. State the formula of the fragment that is removed from the molecular ion to form this big ion. So it's trying to be sneaky here. So what they're trying to say is what's the what's the other? So there could be the ion that produces the base peak. They want the other stuff. So what's 88 minus 57? 31. So I want to find something that's 31. That's C2 24H7. Um, it's probably 345. Okay, cool. Probably need an oxygen in there or something like that then. 31. Um, Cool. So let's draw out. So C, 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 O, H. The way in which I like to do this, generally speaking, is I just create breakages. So if we were to just take this for now, that'd be 12, 13, 14, 14, oh yeah, 16, 30, 31. Oh, perfect. Okay, so then this would be 57 then, which is the base peak. But they're asking for the formula of the fragment that's removed from the molecular ion to form the base peak ion. Oh, oh wait, maybe not. To form the base peak ion. So the formula that's removed to form the base peak ion. So it is 57. Um, if it's removed, I was just, or maybe, yeah, like, yeah, so if it's, so this has been removed so that we can form the base peak ion, I think. So C, 1, 2, 3, 4. So CH4, or biggest thing here is to make sure that you're writing the plus there. So you need to show that it has lost an electron, which is why I can actually go through the mass spectrometer in the first place. Identify one feature of the 1H nuclei that enables peaks to be produced. Um, so you'll notice that we deal with 1H or 13C, and that's just because of an odd number of nucleons. Okay. So I don't want to get too nitty and gritty with it, but generally speaking, if we had an even number of nucleons, then there would be no distinct spin, right? But because we have, if we only have one nucleon, then we have actually a distinct spin. Draw the structural formula of chemical P. If there's only three environments, are we still working on this? Okay, so if there's three environments, five carbons, then there's probably just going to be something like that. Um, so one, two, three, four. So that's what is that? One, two, three, four environments. We need three environments. So let's put another carbon there and an OH. So these are all part of the same environment. Two and then three. So one, two, three hydroxyl group. Let me draw that up properly. Most of the time with mass spectrometry questions, it's good to just draw them in pencil first. It's really interesting, right? Because you could go through all this pain, forget to write the H's, and then you lose your marks. Explain with reference to the structure of chemical B why there is a singlet around 0.9 ppm. Because it's associated, so because a 0.9 is referring to these guys. And the reason why they're a singlet is because their associated carbon, which is this guy, has no hydrogens. Peak at 0.9 ppm. It refers to the RCH3 environment, given that the adjacent carbon that it is connected to has has no hydrogens connected to it. It is displayed as a singlet. Because n+1 rule. So it'd be 1 equals to 0 plus 1. Okay. So we've kind of made reference to the n+1 rule there. Cool. I will probably, so 1, 2. So I'm going to do that in the next part. So I'm going to do question number, oh wait, I can do this. Cool. So write the balanced thermochemical equation. Remember, it's at liquid, um, because it's happening at SLC. So that's 1625, 25 over 2. And then octane minus 5470. So then delta H. 1 mole, calculate the temperature of CO2 in the cylinder. Okay, so if 1 mole of C8H18, we're trying to figure out the moles of CO2 then. So it'd just be 1 times 8, which is just 8. And then the temperature, so PV equals to nRT. Therefore, T is equal to PV over nR. Therefore, 255 times by 100 over 8, is it? Because it's 8 kinds. 8 times 8.31. Cool. Um, yeah, I think, yeah, cool. Um, Now that would be 384 Kelvin. Now, have they asked for degrees? I don't think they haven't asked for degrees Celsius, so I think we're okay. So just remember the temperature is normally in Kelvin. Um, yeah, a tank contains 11.75 liters of water at SLC, 34 grams of C12H6 energy. Sorry. Ah, okay. So Q equals to MC delta T. Now, the reason why I think it's 4 marks is because before the density of the water used to be different, but now it's the same. So it'd be 11,750 because you have to convert it to milliliters. Maybe you have to show that. Do I have to show that? Okay. Um, so I'll just say, so that's a change they made to the study design, but I'll just say given density, uh, 1 gram per mil, right? 1 gram per mil, therefore 11.75 liters is equal to 11,570 grams. So Q equals to MC delta T, which is 11,750 times by 4.18 times by, where is the initial temperature? So that's that. And we get the initial temperature. Oh, yep, sorry, yeah, SLC. So SLC is 25. So that's 57.2 minus 25. So what's that? And that's in joules. So let's just times it by 10 divided by 1,000 because we wanted to get it in kilojoules. Okay, I think that's like the place in which people bleed at the most marks. 11,750 times 4.18 times by, in brackets, 57.2 minus 25, close the brackets. And then let's divide it by 1,000. Cool, 1581.503 kilojoules. And then we want to find out the delta HC of C12H26. So let's divide this guy by 34 grams, 34.0 grams. And we should get something like 46 kilojoules per gram. Um, okay, so generally speaking, petrodiesel, probably not renewable petrodiesel, is distilled from crude oil, which is formed from the fossilized remains of the marine bed, thus has thus has very limited and thus has very limited and thus is in very limited supply as it takes millions of years to form. On the other hand, biodiesel is sourced from renewable plant matter that has a higher rate of production consumption and thus is more renewable than petrodiesel. Um, was meant by the hygroscopic. So it's just the ability of a fuel to attract water. I explain the differences. So biodiesel obviously has the ester functional group, petrodiesel doesn't. So biodiesel is more hygroscopic, given due to its ester bond, which allows it to form dipole bonds with water, as opposed, on the other hand, petrodiesel has a long non-polar hydrocarbon chain, and it thus it cannot, which only forms dispersion forces, and thus is unable to form bonds with water. Cool. Pretty easy. Cool. Sorry, this handwriting was very messy, but hopefully that's correct. Okay, so I'm gonna go through question number 5 and question number 9 and 10 in the next time. Okay. But I hope you guys enjoyed that video. Thank you.